Today we're going to talk about the difference between a differential rate law and an integrated rate law. We've already talked about a differential rate law. So for these purposes, we're just going to talk about a reactant A for everything we're doing today that's becoming some sort of product. So if that's the case, we've written rate laws before. So rate equals K times A to the 0 power. In other words, rate equals just K, because A to the 0 power is 1. If it was first order, we would write it rate equals K times A to the first power. And if it was second order, we would write it rate equals K A to the second power. So this is when we have have determined differential rate law. At this point, we know rate and concentration. So those are the two things that we can use in these equations and do some calculating. If we have the rate constant, we can calculate one or the other. Or if we have the rate and the concentration, we can calculate the rate constant. As far as integrated rate law, for those of you in calc, some of this is going to make a little bit more sense. Now we're going to have concentration in time. We're going to integrate this. And by integrating it, and it's okay if you don't totally understand what that means, but essentially we're taking the change of things over time. So that's what rate is, change over time. But we're going to end up by integrating it. Our equation that we're going to end up with is going to be A, the concentration of A at any time t is equal to A naught, which is my concentration at time 0. I know that my pen is big here and it's tough to read it, and that's supposed to be a T. So my concentration at any time t is equal to my original concentration minus my rate constant times the time. If I integrate the first order reaction, I get the natural log of A. Again, it's at time t. I don't need to write that, but that's not how you'll see it on your green sheet, but I'm going to go ahead and write it for now. And that's equal to negative KT plus the ln of A naught. Naught being time 0. So here's your rate constant. This is the T that's lined up for what the concentration is. And this is the natural log of my original concentration. So A being my reactant and its original concentration being A naught or A0, but it's typically said A naught. And if I integrate this one, I get 1 over A. Boy, that's becoming a mess. 1 over A, again, that's at a certain time t, is equal to KT plus 1 over A naught. So you're going to have to just trust me. My calculus is rusty, but if I integrate this, if I integrate the differential rate law, this is what we get. So it gives us a tool to analyze concentration in time based on the rate law, what's going to happen to the concentration of the reactants over time. So if I graph these guys, and this is time, you can see here that this looks a lot like a y equals mx plus b equation. Y is my concentration, and you could rearrange this a little bit. It would make it a little bit easier. This is my m times x. As you can see, t is on the x-axis here, so it means my slope is negative k, so it's going to look like this. It's supposed to be a straight line. That's my slope, negative k. A naught would be my original starting point there, my original concentration at the beginning. That's A naught. So it's going to go down. It's going to be a straight line. In this case, if it's 0 order, it would just decompose or break down or turn into products at an equal rate. If I do the same thing and graph this guy along the same lines, natural log of A is going to be on the y-axis. I'm going to eliminate brackets just for that's supposed to be a straight line, and this is negative k. So along the same lines, y, mx, so this is my slope. I could have easily just rearranged this. This is what it looks like on your green sheet. So if I rearrange this, it might make this one a little bit easier. A equals A naught minus, oh my gosh, I just screwed it up again. A equals minus KT plus A naught. So we can kind of see that looks like a little bit more like an mx plus b equation that I'm relating to here. So now the natural log versus time gives us a straight line. And in the last one, the second order, I've rearranged a little bit better, but now I'm going to have a positive slope, so that's my k. And this is 1 over the concentration. And then my t is on the bottom again. And the reason why k is a positive slope now, because it's 1 over. So let's just say I started at a concentration of 1. Now that's 1. Well, my concentration of my reactant is going to go down. So let's say it goes to 0.5. Well, 1 over 0.5 is now 2. So that's why it's going up over time. So both of these would go down over time. This one would go up, but a straight line nonetheless. So a typical question that would be asked by AP is a question like, they would give you a graph or tell you that the natural log versus time is a straight line, and from that they would expect you to know that it is a first order reaction. Or you might have to actually kind of think about graphing it, and I'll talk to you about that here in a tiny bit. Zero order, an example, I talked about this one in class, but digestion of alcohol is an example, and that is how it doesn't matter the amount of alcohol, but the digestion by your liver is not affected by the amount of alcohol, but it's affected more by the amount of oxygen in your body. Radioactive decay is an example of first order. It's always first order. Radioactive decay. And in my head right now, I don't have a great example of this, so I'm not too worried about it. Now the half-lives of these, really what you can do to solve for the half-lives of any of them, I think I'm going to erase for now and just put the equations up real quick and then find my half-lives. So like for instance on this one, A equals negative KT plus A naught. So assuming that those are concentrations, I just don't have brackets around it right now. This is ln of A, again that's a concentration, equals negative KT plus ln of A naught. And then this last one, 1 over A equals KT plus 1 over A naught. All the A's are concentrations, and when it says A naught, that's its original concentration. So if I want to do a half-life, in other words, how long it takes for the original concentration to be cut in half, I can rearrange this a little bit and solve for T. But how in the world am I going to do that? Well, I'm going to show you the process, and then I'm going to end up just for one of them, and then we just end up putting the equations down here for the others because the process is pretty much the same. You just got to do some algebra and solve for time. So what would I do for A? I would do half of A naught, or I'll just do that, 1/2 A naught, because that's what we're trying to solve for. How long before half of A, my original concentration is gone? Okay, so that's the first step. And now if I subtract A naught from each side, that gives me negative 1/2 A naught equals negative KT. I'm just going to divide both sides by -1 and get rid of that negative sign. And now if I want to solve for the time that it would take to do that, I'm going to take both sides divided by K, which gives me A naught 1/2, I guess, 1/2 A naught over K. So that is the half-life of a zero-order reaction. half-life equals 1/2 A naught over K. So you could derive this. You're not going to memorize this. On your green sheet, if you do the same thing with this one, your green sheet has 1/2. Actually does not depend on the original concentration at all. It only depends on the rate constant, so it's 0.693 divided by K. That 0.693 comes from taking the ln of 2 through this process. This is on your green sheet, so you'll get the first order half-life equation, but you won't get the other half-lives. And we'll do a little practice for how you would get a half-life with some of the other ones in a bit here. This ends up being K times, or 1 over K times A naught. So this is also in brackets officially, but whenever I have A on here, it's a concentration. Concentration at a given time is this A, right up here. That's concentration at this time. A naught is always my original concentration. These are the half-lives equations. We are going to next apply this information, trying to use the differential rate law or the integrated rate law to solve some problems. So now we're going to apply this to an actual problem. Before, when we discovered the rate law, we did it with concentration and rate data. That is still something we need to be able to do, but we need to be able to figure out the rate law depending on the data that is given to us. So if we're going to have concentration and rate data, we can still do that, look at what happens to the rate based on the concentration. If the concentration doubles and the rate doubles, it's a first order reaction. But that's not always the data given. In this case, we have time and concentration data. So when it says determine the reaction order, it's a challenge in this case because they're giving us only concentration. But remember, depending on what the straight line gives us, that determines the reaction order. So what I would typically do is I look at the difference here. If it's a straight line, every interval of time being 60 seconds here would give me the same interval or change in concentration. And I can see here already that that is not occurring. If I take the 1 minus 0.683, that gives me 0.3 something. If I take 0.683 minus 0.518, gives me 0.1 something. My difference each time is not the same with the concentration versus time. Then I would do 1 over the concentration, so 1 over NO2. Now I just write out the first 3 for myself. So like this is 100, this is 146, this is 193. All I'm doing is taking 1 over those values. This is 239. I can also take, because if 1 over the concentration versus time is a straight line, that's a second order reaction. And I can take the ln of NO2. So ln of that is negative 4.61. Ln of this is negative 4.99. Ln of this is negative 5.26. So let's go to my calculator, click in the natural log button, and plug in that value. So what I'm trying to look for is a situation where the change, because here the change in time is always 60 seconds. So if it's going to be a straight line, that means that my intervals between these are also going to be equal. What I mean by that is if I look at the difference here, this is a difference of 0.38. And this is a difference of 0.27. Well, those aren't the same differences. Here, I have a difference of 46. Here, I have a difference of 47. Here, I have a difference of, ooh, math is hard. Looks like 46 again. So while they're not exactly perfect, it's really, really close to a straight line. They're pretty much exactly the same. So that means that it is second order, because if I graphed it, the 1 over the NO2 concentration versus time would give me a straight line. It'd actually be like that. And how I can tell that is because the interval of time, if you could put this in your calculator too, it would work. But this is a method that I use to just do a quick little, difference. If the difference is the same all 3 times, that tells me, Okay, that's going to be a trend. Here the difference is already wasn't the same twice. Here it wasn't the same twice, so that tells me that this is going to be the straight line. If I write the differential rate law, that is going to be just like we did in the past. Differential rate law, or regular rate law, is going to be K rate equals K times NO2, which is my only reactant, to the second power. In determining the rate constant, however, I cannot use that equation. To determine the rate constant, I'm going to have to use the integrated rate law for a second order reaction. And the reason why is because all the data I have here is time and concentration. I don't have a rate information to throw in this equation and solve for K. So I'm going to have to use my second order integrated rate law to figure that out. So if we go back to that sheet we just filled out, the second order integrated rate law, I'm just going to fill that up or put that on here real quick, is 1 over A, and that's a concentration at time t. I don't always put it in brackets, but I'm going to with this first one to make sure that you see what I'm doing, plus 1 over, or so that's equal to KT, 1 over A naught. So what's it want us to solve for? It wants us to solve for K. So we're going to plug in the data for, we can do any time really, because it's a constant, it should not matter. So I'm going to use just this first 60-second mark. So if I plug in 1 over the concentration at 60 seconds is this. So I'm going to go ahead and just put that in decimal form. And that is equal to K, which I don't know, 60 seconds. I need to actually put this units on here. So this is molar plus 1 over my original concentration, which is 0.00100. It just helps me know my sig figs here. Kind of screwed me up. Really, I should think about all these having 2 sig. Put a dot there, then everything has 2 sig figs, or that would have 3, I guess. But this is molar also. So if I rearrange, this ends up being 146 by taking 1 over that. So I'm gonna take the 1 over. So this is 146 molar to the negative 1 equals K times 60 seconds plus 100 molar to the negative 1. So now I'm going to subtract 100 from both sides. So I'll get rid of this, subtract it from both sides. It gives me. So I did some rearranging and some erasing. Essentially, I have 46 molar to the negative 1 is equal to K times 60 seconds. So if I want to solve for K, I'm just going to have to divide both sides by 60 seconds, and I'm going to get 0.77 molar to the negative 1 seconds to the negative 1. And that would be my rate constant, but it's just another way of solving for it. Now the half-life problem. If you look at the half-life that I gave you on the last sheet, you can figure out the half-life now. I'm just going to scroll up here. So determine the half-life. So I'm going to give you, on the last sheet, I gave you T, and I know you won't have this, but we're going to solve a problem next. You're like, this isn't on my green sheet. How is this helpful if I don't have this equation? Well, you can use it on any of these problems to start with at least. But T1 half is equal to 1 over K, which we can see is 0.77. Molar to negative 1, seconds to negative 1, times the concentration, the original concentration, which is 0.01. Molar. Notice all the molars are going to cancel now. And I take 1 over those numbers, that gives me a certain amount of seconds, which in this case, the answer is going to be 130 seconds. So seconds goes back onto the top. When I divide it, that would be the half-life, or in other words, how long it takes for half my original amount in this situation, which is 0.01, how long it takes for my original amount for half of it to decompose or break apart. Now the last two problems. These are typically a little bit more of challenging. So I'm going to look at my original equation, my 1 over a. Notice how I'm not doing the brackets right now because I'm being a little bit lazy and time kind of is a crunch. It says to use up 90% of the reactant. 90% of the reactant is used up. So based off of that, that would tell me that a tenth of it is left, or 0.1 of it is left. So I can rearrange this a little bit. Actually going to do this first. 1 over 0.10 a naught, because I'm looking for the time it would take before I would get to 90% of it used up. So that means I have 10% of it left. So my amount at time t that I'm trying to solve for is 0.1 of my original. And we're going to see here in a bit why we want to do that. That gives minus, I'm going to subtract this, rearrange a little bit, equals kt. So essentially I am able to solve for a naught, or I can eliminate a naught here a little bit. I can put in my amount because I know that I started with 0.01. So I can go 1 over 0.1. I can actually put that in right away. I could have put in a tenth of a naught, which is just 0.001 minus 1 over 0.01 equals k, which I know k is 0.77. But even if I don't know a naught, I could use this method because the a naughts could end up dropping out. And then I'm trying to solve for t here. So in the end, this is 100. Sorry, this is 1,000 minus 100. These are molar. Sorry. Molar to the negative 1. So this becomes 900 molar to the negative 1 is equal to 0.77 molar to the negative 1, second to the negative 1, t. So when I divide these, 900 divided by 0.77, the molars are going to cancel out and the seconds will flip to the top again, and I'll get my time to be 1169 seconds. And I know it looks like my sig figs have got some issues, but the solving of it is more important because I should have like 90 with a dot or 90.0, so I know I have the exact sig figs. But essentially, I'm just trying to find out the approximate time. If I was going to produce 75% of the product, that would mean that 75% of my reactant is gone. So it'll be 0.25 a naught. That would be left. So it'd be the same process, but using 0.25 a naught instead of using the 0.1 a naught. I'd have 0.25, or a fourth of it is still remaining at that time. I would like you to try the back. I just want to show you something real quick that you'll be using on the back. And because I'm going to give it away, the back is going to be first order, but I want you to determine how that was found. But when you're doing that, ln of a, I'm going to just give you this equation real quick. Oops. Ln of a naught. Let's say that I have, I'm trying to figure out how long, again, let's say I'm doing 90% on the back, which I am at one point. So if I didn't know my original amount, I know I do in this case, but if I didn't, because this will happen where you don't know the original amount, but if I didn't know my original amount, ln of a minus ln of a naught, some of you have worked with natural logs already, is equivalent to ln of a over a naught. is equal to negative kt. Why is that important? Because if we're doing ln of 0.1, which is how much is remaining, a naught over a naught, these cancel. So I don't even need to know my original a naught. And even if I did, I wouldn't have to put it in my equation. I can just drop out the a naughts because of that. So it allows me to manipulate it a little bit different way when I have the ln's like that, and you will see problems like that. So I want you to work on the back of the sheet, trying the same types of steps that we did on the front.